Ailton Rodrigues. He has a master's degree from the University of Minas Gerais in the purification of phosphoric acid, and he is also a consultant for Cefert, a company specialized in fertilizers and processes of fertilizers, granulation of calcareum or lime, and phosphogypsum. Sorry, and gypsum. Good morning, everyone. Well, plants need a lot of nutrition. It's not just your regular bread and butter, right? So here we have mostly six macronutrients and 8 or 10 micronutrients. What's important is that all of these micronutrients, except one, they come from geological resources. What would they be? First of them, this exception is nitrogen. In agronomics, we have the Libigi law. What is Libigi law? Libigi says that if one element, a micro or micronutrient, if it's missing, this is the limitation of production. What is the first element, limiting element that we have even more than water? It's phosphorus. Without phosphorus, there is no grain production, and with no grain production, there is no food. If there is no food, of course, we don't have life. So, we have basically these macronutrients: nitrogen, phosphorus, and potassium. And then we have the secondary macronutrients, which is calcium, magnesium, and sulfur. And here we have the micro. I didn't put all of them on the slide in this presentation, but one of the very important micronutrients is silicon. Silicon is what hardens the plant, especially rice and wheat. If we don't have silicon, the plant will not stand up. And so we're going to talk about these three main nutrients: nitrogen, phosphorus, and potassium. Ammonia is the base of all nitrogen fertilizers. So, nitrogen comes from where? It comes from the air, at least right now without any taxes involved. Can the plants absorb nitrogen from the air? Yes, these are the legumes, which is the case of beans, soybeans. They have other processes. They absorb it from the air. But the grass plants, such as corn, is not able to absorb atmospheric nitrogen, the molecular nitrogen. So they need this nitrogen in an ionic form in order to be absorbed. So the base of the nitrogen chain is ammonia. And ammonia, 82% comes from the air, and 18 come from H2. And H2 comes from where? What are the main sources of H2? Natural gas, GLP or naphtha, the coke gas and coke gas. And here we have some more, the CH4 plus water. I have CO plus 3H2. The second reaction here as well, CO2 plus hydrogen. So, in summary, here we have the energy consumption. What would be today the most efficient raw material for nitrogen? It's the most common is natural gas, but Brazil doesn't have it. The next is naphtha, heavy oil, and coal. China produced a lot of ammonia through coal, but in terms of energy, that is the worst source. There is a unit here in Brazil, in Paraná, called Araucária. It works with this heavy oil, which is also not a very good raw material. And now everyone's beginning to talk about green hydrogen. What is green hydrogen? Yesterday I saw an article talking about green ammonia. It's very interesting. Hydrogen or any other input, that it's interesting that it has the lowest consumption of energy possible in its production. However, at some point, the chemical is not the most economical, right? So we talk about hydrogen as clean energy. However, we are still working that in the lab, right? So it's at the bench level. The main Who is able to produce a lot of ammonia for us? The Arab countries and the people who have natural gas in abundance. So why don't we buy ammonia from there? We're going to discuss that a little later. In terms of investment, the natural gas, considering the reference of one, we have naphtha, which is 15% more expensive. We're talking about capex. Heavy oil is 60% more expensive in terms of capex, and for coal is 2.40. So we see that it's economically not very viable to produce ammonia through coal. But who doesn't have another solution will produce ammonia through coal. We did a work on Valley in a project where we studied the production of ammonia through coal. But the numbers are presented here. Ammonia, urea, the next nitrogen product is urea in the nitrogen chain. What's interesting about it is about its handling. I think that everyone here knows what's urea, right? It's not a very complex process as the ammonia. And what's important is that urea is a great consumer of CO2. 730 kilos of CO2 per ton of urea. This is interesting. And ammonia, on the other hand, 1.8 tons of CO2 are issued by ton of urea produced. Tanto faz, Mônica. It consumes part of this CO2 for the production of urea. Let's go to the P now, phosphorus. We have the rocks, especially the phosphate is classified in three types of rocks: magmatic or igneous, and Brazil represents a lot of these types of rock; sedimentary rock, that Morocco is the main representative, the main producers; and metamorphic rocks that are in the interface in between these two types of rocks. Now, talking about apatite. Apatite, we have the calcium phosphate, which is primary apatite, and then we have secondary apatite, that is COP2O5, varying relations. And between the primary apatites, we do have first fluorapatite, which is the largest representative, hydroxyapatite, carbonate apatite, and as an example of chloride apatite, we have a deposit in Africa that has 1,200 ppms of chloride, whereas the national rocks, Brazilian rocks, the content of chlorine is very low. And here We have the relation between CaOP2O5, that is for apatite phosphate. Above this value, you have carbonates that are not bound to the calcium and the phosphorus. And here in the second equation, you have presence of iron and aluminum. We have kinds of deposits, the content of the feeding during the beneficiation. Uh, This is a range that goes from 12 to 17% for sedimentary rocks and 4 to 12 for igneous rock. 4 it would be in Salitre or Carachi, and in Araxá, Catalão, they have up to 11 to 13%. The content of P2O5 in concentrate is 28 to 32. For sedimentary rocks and for igneous rocks, 32 to 36. The inferior number is about the recovery of the fine simple flotation processes. The mass recovery is from 20 to 30 for sedimentary and from igneous 15 to 23. And the recovery of P2O5 is in sedimentary rocks is 55 to 80 and in igneous rock around 70. This is a visualization of the sedimentary phosphate in Biovar. The deposit is constituted by layers, 7 or layers that are above and then 2 layers down beneath. This phosphate that you can see the darker color is it interfaces basically with diatomite. The mining process is very simple, it's very friable material, so the beneficiation process is also simplified. This is a flow chart of the beneficiation of Biovar, and this is basically a de-sludging of the product. This Biovar deposit has been worked by Jacob was worked by Jacobs in 1960. But why didn't it move forward? Why did it, because the amount of water that they had, the water that they had available was from the sea. So to de-scrubbing, you use the seawater, and that has chlorine, and you cannot decrease the content of chlorine to the necessary levels for commercialization. So the main work developed was to work with the desalination of water, taking the seawater, desalinizing it, and using it in this scrubber system. So after the scrubbing, then dislodging, it goes to filtration, where you use a desalinized water to bring down the content of chlorine. And still, you have this liquid in the interface of the particles. But when it leaves the beneficiation process is around 1300 1400 of chlorine, and after the washing is 700 ppm of chlorine. This is the traditional process for beneficiation of phosphate ore. I didn't talk a lot about rock formation. I'm not good at that, but there is a lot of difference in terms of releasing apatite. Apatite, due to this its igneous origin, it's very crystalline. So in the, I don't know, 85 million years ago, the earth was cooling, so the apatite became very crystalline and with a very flat surfaces. But the sedimentary phosphate, it's different. It's like a porous, it's much more porous. So this is one of the justifications for the natural reactivity. We are going to talk a little bit about that. The process of beneficiation through flotation for igneous rock, you really need to work a lot on the release of these particles. Here, the process is more intensive in terms of energy and also for dislodging. Here we have a comment about the phosphate from the city of Ahaias. I will skip this slide. Bruno is going to talk more about that because he knows much more than me about geology. But I would like to mention the solubility values that we have here. The phosphate from Ahaias is highly reactive. What does that mean? It has how much citric acid or phosphorus soluble in citric acid do you have? So here we have two analyses, and in yellow you have the ratio of P2O5 in citric acid to P2O5 total, and that is around 35%. So these numbers are very, very high, and you have here a scale of several numbers and the content going from 30 to 40%. If you compare with igneous phosphate, it's 2 or 3% the solubility. Here we have a process route here where the apatite is solubilized through an acid media, like a star said, with hydrochloric acid as the agents, solubilizing agents. But you also have the thermal route where the secondary phosphates, you cannot solubilize secondary phosphate with sulfuric acid due to the high presence of iron and aluminum. So you can go the thermal route. And we did a project in Pará for solubilizing secondary phosphate. And the conversions were very high in the reaction. Unfortunately, I will have to go a little bit faster because the time is of the essence. Here I'm going to talk a little bit about phosphoric acid. Star mentioned the reactions here, so I will skip a little bit. It's a reaction of the sulfuric with apatite in an agitated vat, keeping the content of sodium and so on and so forth. These are the main routes: dehydrate and also hemihydrate. The processes and the technology varies, and the efficiencies are always above 92%. The quality of the acid does depend a little bit on impurities, but usually this dihydrate is gives you a more pure product. In the hemihydrate, you have higher temperature, more activities, and higher solubility of this contact. Here are some images of the crystals. We used to see it in a microscope, but now we have the SEM to work very well with phosphate. Let's talk a little bit about potash. Here we have Sylvita as the main source of potash, and the process is a beneficiation, of course, where I break the pulp of this salt with a saline solution, and I also have the comminution process, the flotation process, and finally drying and compacting. Now let's talk a little bit about polyhalite that is from England, and it will probably come to Brazil. Polyhalite is a very large deposit, very old deposit, 260 billion years ago, and it's very, very low. And the evaporite is 70 meters. This is a very interesting project where we have a dry mining at 1,500 meters of depth. This operation and production and maintenance, and this material afterwards is pulled to the 250 meters where we have a 38 kilometers tunnel to transport the material directly to the beneficiation plant. the composition of polyhalite is very interesting. I will show in the last slide the importance of this plant. The production capacity is from 5 to 13 million tons. 2 or 3 will be destined to Brazil, and it's a very high investment, $9 billion, and the project will start in 2027. Here is a work for you, Star. I received a few days ago a consultation from an entrepreneur from agribusiness who's working on regenerative agriculture. He said, I don't want to use potassium chloride anymore. I want sulfate. I want potassium sulfate. And this I did as a suggestion. The potassium sulfate, the only way we can produce that chemically is making a reaction between the chloride and the sulfuric acid. You create a hydrochloric acid, and what am I going to do? I don't want excessive chlorine. So we have to work in a concentrated process in which you have phosphate rock with water, you acidulate, you produce phosphoric, because is it possible to do that from chloride? Yes, it is. Israel knows how to do that. I create calcium chloride instead of but the only condition here is that we have to be close to the sea to do that. I would like to thank the FOSS for the invitation that they made and to the organizers of the event. Thank you.
Congratulations for your presentation. Due to the time, I'm going to invite those who are interested in asking a question. Why don't you ask him during lunch, okay? Please ask your questions during lunch.